Today's lecture on 6.2 comes from homework 15 on My Open Math. There are no textbook problems assigned for this lesson, but I highly recommend you look through the examples in 6.2 in the book because they are good examples. Okay, so let's start with question number 1. Really basic equation. Suppose theta is equal to 5 over 6. Then what is theta equal to? So we have to look a little bit more at the directions here. First of all, theta is in degrees. That's a pretty helpful thing to note. And we want to list all solutions between 0 degrees and 360 degrees. Now notice we do not have arc sine. We have the regular sine function. So we're not limited to the moon of the previous lesson, that is the range from negative 90 degrees to positive 90 degrees. Instead, we're going to be looking at the whole unit circle. Okay, so now remember that the sine value corresponds to the y value. So on the y-axis, this point right here at the very top has a y-coordinate of 1. So 5, 6 is about right here. Now there are 2 points on either side that have a height then, a y value, of 5, 6. This value of 5, 6 is not on the unit circle in terms of an exact solution. And you'll notice here anyway it says rounded to the nearest whole number. So what we have to do is use the calculator. But when we use the calculator, we'll end up using the sine inverse button. And when we use the sine inverse button, we'll only get one result. That result will end up being in the first quadrant because of this being a positive number. So let's go ahead and do that. So here's a free online scientific calculator that I found. Sine inverse then of 5 over 6 is going to be 56 degrees if we round to the nearest whole number. So 56 degrees will be one of our solutions. So we'll go ahead and label this point right here 56 degrees. This will be one of our 2 answers. Now note the angle that is formed here, this 56 degree angle here, would need to be congruent to the angle over here. So these are both 56 degree angles. So then how do we get this value right here? This value then is 180 degrees minus 56. So that's 124 degrees, right? 56 degrees and 124 degrees. Okay, so let's do another one just like this. This time I'll do question number 2 and I'll do it on the board. Here we have the sine of theta is equal to negative 1 over 15. Notice we're still in degrees. Always pay attention to what mode you're in. Okay, so here's the problem. Sine of theta is equal to negative 1 over 15. So negative 1 over 15 is not very far down, right? So we have a point right over here in the 4th quadrant, and then a point over here in the 3rd quadrant. Now when we use the sine inverse button, the sine inverse button is going to give us a value only in the 1st or 4th quadrant. And furthermore, since it's going to give us a 4th quadrant value, it will actually give us negative degrees, which in the end we won't want. But let's at least start off with that. So now we'll go ahead and flip back over to the calculator. And we're going to do the sine inverse of negative 1 over 15. And this is in degrees. Oops, that was not supposed to happen. Yeah, there we go. Negative 3.8, that's roughly negative 4. So we would say then that this value right here is approximately negative 4 degrees. We can't keep negative 4 degrees because negative 4 degrees is not between 0 and 360. So what we want to do is simply find something coterminal with negative 3 degrees. So add 360 degrees and we'll end up with 356 degrees as one of our 2 answers. Now if the angle right in here, this little tiny angle, is a 4 degree angle, then over here you also have a little 4 degree angle. So how do you get this value right here? You simply add the two pieces together to make a whole. So the first piece of this angle is the 180 degree angle that starts at the positive x-axis and goes to the negative x-axis, right? Then you add on to that 180 degrees, the 4 degrees, and you get a grand total of 184 degrees. So we have two answers, 184 degrees and 356 degrees. So switching back now, we've got 184 degrees and 356 degrees. As you can see, it doesn't matter if you list them from least to greatest or not. The point is, though, to pay attention to the directions. Notice we're in degrees. See that we want solutions between 0 and 360. See that we are rounding to the nearest whole number. Always pay attention to those directions. Now, throughout this homework, you'll see that I keep pushing you back to the textbook. Even though there are no assigned problems from the textbook, using the textbook as you go through your homework is a really wise idea. In fact, it's a really good combination to go through the homework using your textbook, the lecture, and also the question helps. You have multiple paths to learning here. You really want to understand what you're doing. The more you understand, the less you have to study later. Okay, so now we're going to go to degrees as well, but this time we're going to give all solutions, not just those between 0 and 360. And this value right here of -1/2 is, of course, on the unit circle, so this really won't be so bad. The sign value at -1/2, we've got two of those values. We've got one down here and one here. And since we're using all possible answers, it doesn't matter if you choose for this one to be -30 degrees or if you choose for it to be 330 degrees, it doesn't matter. You're going to be using multiples of 360 on top of that, okay? So let's say, so of course this one over here is 210 degrees. These are unit circle values. If you want to use 210 is a natural choice because it's between 0 and 360. And then we're going to add all multiples. We're still in degrees, so instead of 2 pi k, you need to add 360k. That's saying that you're going to go around the unit circle k times, and k can be an arbitrary integer, so it could be a negative multiple of 360 or a positive multiple of 360. You just keep going around and around and around and around, and you'll see every single one of those solutions. It's an infinite number of solutions. And then for the other one, you can choose either -30 or positive 330. It doesn't matter. And then again, you have the plus 360k. Okay, so next let's look at question number 4. Now we have switched over to radians. So you're going to be switching back and forth between degrees and radians. So for every single question, just ask yourself first, is it degrees or is it radians? That's a very important question. And we're only finding the solutions between 0 and 2 pi. And so we need a value of 7/12. All right. And this time, instead of rounding to the nearest whole number, we're giving answers accurate to 4 decimal places. So read through all the directions. Make sure you got all those directions in your head before you get started. I'm going to do this one on the board. Okay, so I need to find the two locations between 0 and 2 pi where the sine of those two angles is equal to 7/12. And since the height here ranges from 0 to 1, we just pick 7/12 here on the y-axis, have a dot to the right and a dot to the left. These are the two values where the sine value is going to be 7/12. And we want to go to 4 decimal places. So what we're going to do is we're going to find out this one right here first by using arcsine with a graphing calculator. So let's go ahead and go over to, or a scientific calculator. We'll go to the scientific calculator and do arcsine of 7/12. And we are in degrees, so we need to switch out of degrees into radians. That's really important. So now I have 0.6228, and that is going to be my value there. Now, I do want to keep this number in mind. I'm going to go ahead and write out a few more decimal places, 265.8, because when I do this next part, I want to make sure that I don't have a rounding error. Okay, so what is the next part? The next part is trying to figure out what the other value is. Now, as in the previous problem, this should look very familiar to you. These two angles are going to be congruent. So this value right here is also 0.6228. So to get here, we just need to take pi. This is pi right here, right? We're going to take pi and we're going to subtract from pi 0.6228. So we can go back to the calculator. So I'm going to take pi, and then I'm going to subtract from pi 0.6228. I'm going to go out a few more decimal places, 2658. Probably just 2 more decimal places would have been fine. Here, I just want to really make sure I don't have a rounding error. So my other answer is 2.5188. And now we'll go back to my open math. And my two values are 0.6228 and 2.5188, just like I said. Okay, so now let's move on to question number 5. Question number 5 and question number 6 are very similar, except that question number 5 is limited from 0 to 2 pi, and question 6 is limited, was not limited, so it's all possible multiples, 2 pi k. So what we're going to need to do is we're going to need to, I'm going to work on the second one because the second one is harder than the first one. So if you can understand how I do question 6, you'll be fine with question 5. So let me go ahead and put this up on the board. Okay, so here's question 6. What you first want to do is get the trig function all by itself, just as though you were solving for x. So if we subtract root 3 from both sides and then divide both sides by 2, we end up with that the sine of x is equal to negative root 3 over 2. And that's why the problem is asking for exact values. Of course, we know that there are 2 places where x is negative root 3 over 2. Those values down here, these are going to be in radians. So this is going to be 4 pi thirds and 5 pi thirds plus 2 pi k plus 2 pi k. That would give us the infinite number of solutions. So now going back to my open math, you see here that they've entered 4 pi thirds and 5 pi thirds in the same answer. So it could look a little deceiving that this is just a single answer, but actually there are 2 base answers that you need to give in addition to the plus 2 pi k, or 2k pi, which is algebraically equivalent. Okay, so let's go ahead and move down to, I've done already something like this, so I think it would be better to go down, let's do question number 9. So here for question number 9, we're bounded between 0 and 2 pi. So first what you want to do for your equation is get the trig function by itself. So now we have the cosine of theta is equal to negative 1/2. And then we've got 2 points here on the unit circle where cosine would be negative 1/2. And this would be pi 6 plus pi halves, which would be 2 pi thirds. And then this one down here is 4 pi thirds. And then you have plus 2 pi k plus 2 pi k. So you always add that 2 pi k on. This is actually not, because we are between 0 and 2 pi. Never mind. This is where you have to really pay attention. Radians or degrees? Infinite solutions or finite solutions? Here we want finite solutions between 0 and 2 pi, so forget these. Okay, there are your two answers. All right, next problem. You have infinite solutions right here, so it's the same type of problem. Okay, so let's do a tangent problem now. No, let's do cotangent, because that's a little harder. Let's do cotangent. Yeah, question 12, cotangent. Okay, so this is cotangent of x, or between 0 and 2 pi. So this is radians, finite solution, so I will put these on the board. So we're going to be looking for cotangent equal to negative 10. So what we want to do first, anytime we have a reciprocal function, is just rewrite this in terms of the original function, tangent. So this is really asking where tangent of x is equal to negative 1 over 10. So as long as you can flip it over, you're fine. The only time you wouldn't be able to do that is if you end up with cotangent is equal to 0, in which case you would want to do cosine over sine is equal to 0, and thus cosine is equal to 0. Okay, but in this case, any non-zero case, you can flip cotangent over and turn it into tangent. So next what we want to do is think about where do we have negative tangent values. Negative tangent values occur in the second and in the fourth quadrant, and they are 180 degrees apart from each other, or pi apart from each other, depending on if you're in degrees or in radians. And here in this particular problem, if you'll remember, we are in radians. So what we want to do is go over to the scientific calculator, and we want to, let's clear this, go to arctan, and we need to do negative 1 over 10. And we end up with a value of, we are in radians, negative 0.09, well, what are we rounding to? We are rounding to 4 decimal places. Okay, so 1, 2, 3, 4 decimal places, and we have to round this 6 up to 7. So negative 0.0997. Okay, so that value right there is not between 0 and 2 pi. So we would want to find something coterminal. So we want to add 2 pi onto that value, all right? So if we go back to the calculator again, we can then take this value and we can add to it 2 pi. And we end up with the value 6.2832. So 6.2832 is rounded to 4 decimal places. Now going back to here, if this is 6.2832, what is this previous one right here? This previous one is 1 pi back from that value. So we simply subtract pi then from that value. Alternatively, you could have started here at this negative value, added pi, written down the answer here en route to adding a second pi. So it doesn't matter if you want to add 2 pi and then subtract a pi, or start here at your negative answer and add 1 pi, write down your first answer, add another pi, write down your second answer. Either way, we'll come back over here and now we're going to subtract pi, and we end up with 3.1411. You know what? I just realized we have not actually included these other values. That's pretty important to do. This looked remarkably like pi. That's because this previous line wasn't even associated with it. Okay, hold on. I have to do enter, and then this is not working. Same line. I am new to this one. Let's try this again. Tan inverse negative 1 over 10. It takes a while to get used to any new calculator, doesn't it? Okay, and then I'm going to have plus pi. That's going to give me my first value. And then, after I write down that first value, 3.0419, then I'm going to add another pi onto it and get my second value, which is now 6.1835. Okay, so first I added my first pi. I added my first pi and got 3.0419, and then I added pi again and got down to 6.1835. So now when I go back to here, you can see these answers, 3.0419 and 6.1835, just as I had found. So that's how you do a cotangent problem. And likewise, when you do a secant problem, you want to rewrite this as the cosine of x is equal to 4 over 7, and then you would use arc cosine or inverse cosine with 4 over 7 to get your first quadrant value, and then you would get your second quadrant value using the same methods as we used earlier. Okay, now we're going to move to some algebra here where we're using the zero factor property. So let's do question 14 on the board. Okay, so our answers for this problem need to be in radians, and they need to be between 0 and 2 pi. The zero factor property, remember that if you have AB is equal to 0 in algebra, that's equal to, then either A is equal to 0 or B is equal to 0. That's your zero factor property from algebra, and we use that when we're solving quadratics, right? So if the quadratic factors. So what we want to do is take each of these two factors and set them equal to 0. So we would have that the cosine of x is equal to 0, or 2 sine x plus 1 equals 0, and then you can further rewrite this one as the sine of x is equal to negative 1 over 2. Okay, so what I would do next is draw a unit circle, and then we're going to put dots on the unit circle for each of these two equations. We have two different equations that we're solving. So where is cosine equal to 0? Cosine is equal to 0 here and here. So this would be pi halves, and this would be 3 pi halves. And then where is sine equal to negative 1/2? Well, that would be here and here. So your four solutions are dots on a circle, and then you can just list them out. So my first one I come to is pi halves. The next one I come to is 7 pi sixths. You can see how knowing the unit circle continues to be really important in this course. So if you have not memorized it yet, I highly recommend you do. Then we have 3 pi halves, and then lastly 11 pi sixths. And that's why my high school teacher made me write out the whole unit circle every day at the beginning of the class for a certain period of time. We had 2 minutes to write out the whole thing every day. That was a quiz we had every day. That's how important it is. Okay, so that's how you do a problem like that. As you can see, the algebra part is easy. The algebra is something that you did way back in Algebra 1, just using the zero factor property. Once you get your trig functions equal to whatever they're equal to, then we revert back to the unit circle and those techniques that we were using earlier in the lecture. Okay, so let's take a look at question number 16 now. We're in radians. We're going from 0 to 2 pi, and we have to solve this equation. So let's do this up on the board. Here's the equation. We're still going to be continuing to use the zero factor property. So what I want to do is I want to get everything on one side and then factor the GCF. I made a mistake here. I wrote 3 costs. Never just write 3 costs. You need to include the variable 3 cos x and cos squared x minus 1. Okay, so if you move the 3 costs to the left-hand side, you can then factor out the 3 costs, and you end up with just cos squared x minus 1. And then you can factor this further. Now, if this were a proof, I would not dare to skip this step in between, but we're not doing a proof. We're just doing some basic algebra solving, so you don't have to be nitpicky about every single line. To go from here to here is not too much of a leap for a student who's gone through college algebra. Okay, so now I'm going to use a zero factor property on each of these factors. So I have that the 3 cos x is equal to 0, or cos x plus 1 is equal to 0, or cos x minus 1 is equal to 0, and then I want to isolate each of these trig functions. Cosine of x is equal to 0, or cosine of x is equal to -1, or cosine of x is equal to +1, and then you draw your circle. And then you put dots everywhere that this is true. So we've got cosine is equal to 0 here, here, cosine is equal to -1 here, and cosine is equal to +1 here. And so my solutions are 0, pi halves, pi, and 3 pi halves, because I'm only solving from 0 to 2 pi. So for the next question, we're going to do question number 17, where we have 18 cosine squared t is equal to 8 cotangent t sine t. We're solving from 0 to 2 pi. Answers need to be rounded to at least 2 decimal places. Okay, so first thing we want to do is we would want to get, well, you want to get everything on one side and factor it, but before you would even do that, you would look across this and say, wait a minute, I have 3 different trig functions. That's not good. So what you'd want to do is get yourself to a position where you could either factor out certain things so that your individual factors, when you set them equal to 0 for the zero factor property, are going to have unique trig functions in them. Or in this particular case, you need to do a substitution. So we're going to rewrite this with cotangent being replaced by cosine over sine. So it's one thing to skip algebra steps, basic algebra 1 steps. What you do not want to do is skip trig steps, steps that are unique to this course. And that would be all of those steps that you used for proofs, where you're substituting one trig identity, or you're using a trig identity to make a substitution. Don't ever skip those kind of steps. Skipping arithmetic, skipping algebra 1 work, that's not the same deal as skipping this kind of work. You do need to show something like this, okay? And then don't ever cross through your work. Well, you can do whatever you want in your rough draft. In your final draft that you upload to me, make sure you don't cross through your work. Okay, so now the good thing is we now just have a plain old 18 cos squared t is equal to 8 cos t, and now that I only have one function, now I will get everything on one side and factor out the GCF. Right, so if you move this to the left-hand side, your GCF would be a 2 cosine t, leaving you with 9 cosine t minus 4. So we use the zero factor property and set 2 cosine t equal to 0, and then we also set 9 cosine t minus 4 equal to 0, and so that's going to give us that the cosine of t is equal to 0, or the cosine of t is equal to 4 over 9. So now we draw our circle. Cosine is equal to 0 at pi halves and 3 pi halves. And then cosine of t is equal to 4/9 at some sort of value in the first and the fourth quadrant. And we don't know what those values are. So this first value right here, though, we can find using the graphing calculator or the scientific calculator. So let's go back over here to the scientific calculator, clear all this. We're in radians still. And we want to use the inverse function of cosine inverse on 4 over 9. And when we do that, we end up with a radian value of 1.11. We only need to go out at least 2 decimal places, and this 0 afterwards makes it really nice just to stop there. Okay, so now let's go back over here. This is 1.11. Then the other value down here, remember that this angle right here is going to have to be congruent to this other angle down here. These are 2 congruent angles. So to get this other lower value, we're going to take 2 pi, this is your 2 pi, and subtract from 2 pi 1.11. And then let's see what sort of approximation we get there. So clear this. We're going to have 2 pi, subtract 1.11, and we have 5.17. So now when I go to list my final answer, I would say that for your final answer, you can list a combination of exact and approximate values. So your first answer is 1.11. But for your second answer, you can list your second answer as pi over 2. Okay, and then you can continue with, so I've listed 2 exact values and 2 approximate values, and that's okay.